So we differentiate and then we integrate. So we differentiate u. So the derivative of u, of course, is going to be equal to 1. F prime, the integral of f prime of u is of course going to be equal to f of u, since the integral is just like the reverse process of differentiation. And then yes, I am serious. In this video, I will show you how to solve the integral of inverse function of x dx. Now, apparently, this is one of the integration shortcut that you may need to be applied when you want to solve an integral. So this is just basically a shortcut. So in this video we will try to figure out what is the solution of this integral of the inverse function of x dx. So now here's what we're thinking. Now if f inverse of x, now we know that f inverse of f of x is equal to x, right? So maybe we can apply the substitution x is equal to f of u, because if we plug in the x equal to f of u here, we will get f inverse f of u, which will equal to u, right? So let's apply the substitution. So we will let x equal to f of u. Then we need to differentiate in order to get dx. So dx is equal to f prime of u du. And then we are going to plug the substitution equation to here, and the dx equation to here. So this whole thing is going to be equal to the integral of f inverse of f of u times f prime of u du. And this, now when we look what we got here. F inverse f of u, that's same as u, right? So this thing is equal to the integral of u times f prime of u du. And then since we got a polynomial time multiply with a function, a random function, any kind of function, we can apply the integration by parts, right? So in order to apply the integration by parts, let me just write down here, here. Now u, we will plug in the differentiate part, because that's normal. Because we sometimes want to make sometimes when we have a polynomial, when we differentiate it, we are intentionally trying to differentiate and then stop until when it gets to 0. So, but I don't think we don't need to do this time, because look what we get here. Now I will let u to be the differential function. Differential function, which basically means I want to have u to be differentiate, and I will have f prime of u to be integrate, and coincidentally the f prime of u, when we integrate, we will get f of u, right? So we differentiate and then we integrate. So we differentiate u. So the derivative of u, of course, is going to be equal to 1. F prime, the integral of f prime of u is of course going to be equal to f of u, since the integral is just like the reverse process of differentiation. And then this thing is going to be equal to u times f of u minus integral of f of u du. And then after that, we are not necessary to solve the integral of f of u du, because this is just a shortcut. So the final step is we are going to undo the substitution. X is equal to f of u. Now x is equal to f of u, but we want to express u in terms of x. So what is the function u expressed in terms of x? Now, based on this substitution, right, if x is equal to f of u, then does it mean u is equal to inverse f of x? Of course it is. So we will undo the substitution for u and f of u. So this thing is equal to x, because we got x is equal to f of u, you got right here, times f inverse of x minus the integral of this. Now unfortunately we don't have any equation for this, but I will let the integral of f of u du equal to capital F of u, and then after we solve the integral such that it will become capital F of u, and then undo the substitution right here, so this will be equal to x times inverse f of x minus f of f inverse of x plus c. So the integral of f inverse of x dx is equal to this. So this is one of the integration shortcut. So the integral of f inverse of x dx is equal to x times f inverse of x minus capital F of f inverse of x plus c, where capital F of x is equal to the integral of f of x dx. So what we basically do is we are changing the inverse function to its original function, like original function. So this is one of the integration shortcut that you may can apply when you need to solve an integral that is so we can solve the integral more easily. Now let's solve the integral of natural log of x dx using the shortcut the shortcut that we derived just now. So as you can see, the integral of f inverse of x is equal to x times inverse f of x minus capital F of f inverse of x plus c. So in order to apply this shortcut, is integration shortcut, I have to let inverse f of x is equal to natural log of x, and then I will let this equal to y. Then switch the variables, then solve for y another again. Sorry, because it's natural log, when we need to go to other side, we will have the exponential, which is e or Euler's number as the base. And then now because we already switched variable, the y that we are referring to now is f of x. So f inverse of x is equal to natural of x, then f of x is equal to e of x. So since we need to apply this shortcut, so this whole thing is equal to x times the f inverse of x, which is natural of x, minus the integral of e to the x. But wait, so we got the f, and remember capital F of x is equal to the integral of f of x dx. We have f of x right here. So in order to have the capital f of x is equal to the integral of e to the power of x dx, So the capital F prime of x is equal to the integral of e to the x times dx. So this thing is going to be still remain the same, of course, which is equal to e to the x. Then f of inverse of x is equal to e, because remember this is composite function. It's like composition between two functions or combination between two functions. So we got capital F right here, and then we got f inverse of x. So this capital F of f inverse of x is equal to e the power of natural of x, which is equal to x. So this term is equal to x, and then finally we plus c. So by using this shortcut, we can tell that the integral of natural log of x dx is equal to x times the natural of x minus x plus c. So this is our final answer. I hope you guys enjoy this video. If you enjoy, leave a like and subscribe to my channel for more upcoming videos, and I will see you guys next time.